to the fourth lecture in Module 8 on numerical solution of Navier-Stokes equations. In this module we have been focusing on the numerical simulation of Navier-Stokes equations. We have discussed its features and explicit and implicit time integration techniques in earlier lectures. We had also discussed some implicit pressure correction methods, and this lecture is a continuation of this category of methods, and we will also consider fractional step methods in this lecture. Before proceeding further, let us have a recap of what we did in the previous lecture. Our main topic was implicit pressure correction methods based on implicit time integration schemes and linearization of nonlinear momentum equations. We discussed one of the most widely used algorithms of this family called simple algorithm. Now, in this lecture we would focus on the improved versions of the simple algorithm. We will take up only two of them, SIMPLEC and simpler, and we will look at a family of methods called fractional step methods. So, lecture outline, we will have a look at the SIMPLEC and simpler methods of the implicit pressure correction methods family, and then we will discuss the fractional step methods. So, now let us come to SIMPLEC method. SIMPLEC is an acronym. We have already seen what simple stands for, and SIMPLEC was essentially called simple consistent because there was a consistent approach to the treatment of Vi prime tilde, which was ignored by Patinker's scheme simple, and this was proposed by Van Duermel and Rathby in 1984. So, what Van Duermel and Rathby proposed was that now let us approximate the velocity correction term which was omitted in simple, and this approximation would be obtained by using a simple averaging procedure, and what they found is it leads to a much more consistent method which converges a lot more rapidly, and we do not have to worry about the under relaxation factors which are required by simple algorithm. So, that was the main attraction of this SIMPLEC process. Computation wise, almost similar set of steps were involved. So, now let us derive the equations which is slightly different from simple. The basic premise of course remains the same, that would still use the equations which we derived earlier for implicit pressure correction methods. And the SIMPLEC is also based on velocity and pressure connection concepts. So, based on the concept of velocity correction and pressure correction, which was introduced by Patinker. That is to say, we would obtain the velocity field Vim as sum of our intermediate velocity field Vim star. Now, this Vim star, remember, we had obtained it using the linearized version of momentum equation, wherein for the right hand side evaluations we have used values of the velocity field and pressure field at the previous iteration. So, that is how we had obtained this Vim prime plus a small velocity correction. You would obtain it as a part of this solution process. Similarly, the pressure field at the current iteration is obtained as sum of the pressure at the previous iteration plus a small pressure correction. And as I mentioned earlier, here we would not require any under or over relaxation for improvement of the convergence. That is the beauty of the SIMPLEC method. Now, what was done in simple scheme? We can do the same thing. So, substitution of these momentum equations. So, substitution of above equations in linearized momentum equation gives that relation, which is basically a link between the velocity and pressure corrections. It is the same equation which we earlier derived for simple method, that is, say V I P prime is equal to V I P prime tilde minus 1 over A P V I delta P prime over delta X I at P. And let us continue the same numbering of equations for sake of consistency, which we used earlier. So, the 8 continues, and we will call this equation as 14. Sorry, this is our previous equation which we had numbered as 9, and where our V I prime P tilde was defined as minus 1 over A P L A L V I prime. So, this was our previous equation which we have written earlier for this tilde variable. Now, in simple scheme we said since V I prime tilde, it is a weighted summation of V I prime L at the neighboring nodes, and these corrections we do not know, so we ignored it. So, instead of ignoring it, now let us first try to get its approximation in terms of the neighboring values. So, now let us introduce that approximation. So, let us assume that the velocity correction at central node or at computational node P can be approximated by a weighted average of velocity corrections at neighboring nodes. That is to say, what we claim is that V I P prime, we can approximate it as a weighted average. The weight factors are our coefficients A L V I, which we have already calculated earlier. So, the sigma L A L V I V I L prime divided by sigma A L V I. So, that is what represents our weighted average, and this is fair enough. We want to find out a correction term which is fairly small, and it is reasonable to assume from the physics that it would be linked or it would be related to the correction values at the neighboring nodes. So, let us call this equation as equation 14. Now, if we combine equations 9, 10 and 14, in fact if you combine 10 and 14, so in terms of this approximation, using approximation 14, that V tilde prime IP can be written as now if we substitute it in our pressure linked equations, thus from equation 9 what we will get, that Vi P prime, this is equal to minus 1 over APVI sigma L or if we transfer the terms, multiply by this APVI and collect them together. So, we get APVI plus sigma L ALVI times Vi P prime is equal to minus delta P prime over delta Xi. Or in other words, the modified form for velocity corrections we get as minus 1 over APVI plus sigma L ALVI delta P prime over delta Xi at point P. So, this is the modified equations for or velocity corrections, which is directly linked to the pressure corrections. So, now next task is to obtain an equation for the pressure correction, and if you look at this equation, what we can clearly realize is there is only one small difference with respect to simple scheme, that is the denominator on the right hand side has changed. In place of AP, we have got an additional contribution coming from the coefficients linked to the neighboring terms, and that is what leads to a much better convergence behavior of the simplex scheme. So, now we have got the form for velocity correction. So, what would the velocity be? So, Vi m, which we have written as Vi m star plus Vi prime, substitute for Vi prime. So, this becomes Vi m star minus 1 over APVI plus sigma L AL VI delta p over delta xi at p. Now, this velocity field must satisfy continuity equation. That is what our contention is. We want to find out a velocity field at the current iteration level which would satisfy continuity. So, VIM must satisfy the continuity equation. This is given as delta VIM over delta xi is equal to 0. Okay. So, if you use this, let us see. So, from 17 and 18, what do we get? Left hand side of 17 now would become delta VIM over delta xi is equal to delta VIM star over delta xi minus delta of delta xi 1 over APVI plus sigma L ALVI delta P prime over delta xi at P, noting that from continuity equation the left hand side becomes 0 and this gives us delta of delta xi 1 over APVI plus sigma L ALVI delta P prime over delta xi at point P. This would be equal to delta over delta xi of VIM star this is now the discrete Poisson equation for pressure correction. Okay, so now we have got all the equations which we need to obtain our solution. We have got our linearized momentum equation which are based on the usage of the values of velocity and pressure field at the previous time iteration, and from there we can obtain our intermediate velocity field VIM star. Now, once VIM star is available, similarly our coefficients APVI and ALVI, these would also be based on the values at previous time step, they are also available. So, we can compute all of these, use it in this discrete Poisson equation for pressure correction, and we can solve for P prime. Once we know P prime is directly linked to the velocity corrections V prime. We had derived the formula earlier for that, which was given by the V prime was given by 1 by APVI plus sigma L ALVI delta P prime over delta xi. So, that formula directly gives us the velocity correction. Add the velocity correction to the velocity VIM star, and that will give us the velocity field VIM at the current time level which satisfies the continuity equation. Add a pressure correction to Pm minus 1 to get the pressure field at the current iteration Pm. So, we are done with as far as the computations are at present iteration are involved. So, now let us summarize our algorithm, and this algorithm looks very similar except for a small difference in the coefficients which are involved in the definition of velocity corrections and the pressure correction equation. compared to the simple algorithm. The computations involved are almost steps are identical. So, the first step is that use velocity and pressure at previous iteration level, that is use Vi m minus 1 and Pm minus 1, or if we are at the first iteration use the values at previous time step, solve the linearized momentum equation to obtain the velocity field Vi m star. So, that is the first step. Next, once we know Vi m star, find out its derivatives, okay. Use it in SIMPLEC pressure correction equation. So, I have put this word SIMPLEC to indicate that now this equation is different from the correction equation for or Poisson equation for pressure correction in simple algorithm. So, let us call it SIMPLEC pressure correction Poisson equation. Solve this equation to obtain P prime, and once we have got P prime, compute the velocity correction Vi prime, then add this velocity correction to Vi m star to get the velocity field Vi m and pressure Pm. Next, there was checking step, that check if velocity field Vi m and pressure field Pm satisfy the momentum equation. If yes, we have now got a converged velocity and pressure field at the current time level, okay. So, set these Vi m and Pm as the values at time level n plus 1 and proceed to the computations at next time level. If not, we have to repeat the iterations again. So, we will increment the iteration counter, m will be set to m plus 1, we will go back to step 1 and repeat the whole process until we have obtained converged velocity and pressure field at the current time level t n plus 1. Now, which I have already mentioned earlier that in SIMPLEC algorithm we introduced an improvement with reference to simple, that there were no omission of any term, that Vi prime tilde instead of being omitted, it was approximated consistently in terms of the neighboring values. So, SIMPLEC converges a lot better than simple algorithm. So, we do not require any under relaxation with SIMPLEC algorithm. As far as computational requirements are concerned, they are almost identical in simple and simpler. SIMPLEC, both the algorithms require same number of almost same number of computations. So, computation time requirements of simple and SIMPLEC are both very similar. Next, let us have a brief look at algorithm which was named simpler. In fact, it is simpler is a shortened form of simple revised, which was proposed by Patanka. So, simple revised and the acronym became simpler. Now, here the Patanka's contention was, look, let us do the computation for pressure correction in the same way as we did in simple, but this pressure correction is used only to obtain the velocity corrections. That is to say, we have got a linking equation, an equation which linked the velocity corrections to the pressure corrections, okay. Use those pressure corrections in that equation to obtain our velocity corrections, but do not add the pressure corrections to Pm minus 1 to obtain Pm, that is to say the pressure at the current outer iteration. Instead, what we will do is that the new pressure field is computed separately using Poisson equation for pressure, in which corrected velocity field is used. Remember, we have derived this a Poisson equation for pressure in our original implicit pressure correction algorithm, wherein the right hand side of this pressure Poisson equation was in terms of Vi m star, that is to say in the terms of the intermediate velocity field. In simpler algorithm, what we do is we already know what is the updated velocity at the current outer iteration. So, in our pressure Poisson equation, instead of Vi m star we would use Vi m, which has been calculated already. Since it is available, let us use it and thereby obtain the pressure field Pm. So, that is one important addition which has been made to simple algorithm, and it leads to significant, very significant improvements in simple. So, convergence is very good of the simpler algorithm, but there is a drawback as well. There is significant improvement in convergence of iterative solution process, but that comes at the cost of the solution of an additional Poisson equation. In simple we solved only one Poisson equation, that is a Poisson equation for pressure correction. In simpler algorithm we have to solve for two Poisson equations, one is for pressure correction and the rest for the pressure field itself. So, in nutshell what we will have to do in simple, we have to solve for 3 sets of linear equations, that is one each for each of the velocity components to give us Vi m star field. So, we have to solve 3 systems of linear equations for velocity fields and one for the pressure correction. In simpler algorithm we will have to solve 5 such set of equations, 3 for velocity field and one each for pressure and pressure correction. Now, let us reiterate the algorithm. So, here there would be an addition with respect to simple, few steps are common, with like first step is common, that use velocity and pressure at the previous iteration level Vi m minus 1 and P m minus 1 to solve the linearized momentum equation to obtain the intermediate velocity field Vi m star. Okay. Now, compute or use this velocity field Vi m star, compute its derivatives and solve the simple pressure correction equation. I want to emphasize here again that we have to use or we have to solve the same pressure correction equation which we have obtained in simple, which omitted Vi tilde primes. So, that term is still omitted. We would use same simplified equations for the pressure correction as well as for velocity corrections. So, using the formula as were used in simple algorithm, obtain the updated velocity field Vi m. Next, what do we do? Use this Vi m now in pressure Poisson equation to solve pressure Poisson equation and obtain the pressure at the current outer iteration P m. By putting this additional step, now we have got updated velocity field which satisfies continuity equation and updated pressure field. Next, our checking step, check if Vi m and pressure field P m satisfy momentum equations. If yes, we are done with the computations at the current time level and we can proceed to the computations at next time level. If not, we would increment our iteration counter and go to step 1 and repeat the set of iterations once again, or these iterative processes once again to obtain the solution. So, as I remarked earlier, simpler has got very good convergence behavior compared to simple. So, in fact, now it is more popular to use SIMPLEC or simpler. SIMPLEC is computationally more efficient because we have to compute only one pressure Poisson equation, or we have to solve for only one of them. Otherwise, their convergence behavior of SIMPLEC or simpler algorithms are almost very similar. Okay. Now, we will move on to a next family of methods. There are many algorithms which have been suggested in literature to solve incompressible Navier-Stokes equations. We have discussed only few of them. We discussed explicit time integration and implicit schemes. We would have a look at yet another set of methods which are called fractional step methods. Now, these fractional step methods are essentially approximate factorization methods. This factorization is fairly similar to what we had seen earlier in the case of ADI method. Say for instance, if we use explicit Euler method to integrate our momentum equation, then in that case the discretized momentum equation can be symbolically represented as Vi n plus 1 is equal to Vi n plus delta t times Ci plus Di plus Pi evaluated using the values at time level n. Now, here we have used these symbols C, D and P. Now, C represents the convective term, D represents the diffusive term which is essentially the terms which come from our stress field, and P represents the pressure gradient term. Now, this particular representation opens a way to a next class of methods. Like, instead of doing our computations in one step, we can break it down in a 3-step method. So, first step, what do we do? First step, let us use the value at the previous time level and only add the contribution of the convective term. This will give us an intermediate velocity field, let us call it as Vi star. So, Vi star is equal to Vin plus Ci delta t. In next step, we will add our diffusive terms. So, let us define a new intermediate velocity field, let us call it Vi star star. So, Vi star star is equal to Vi star plus Di delta t, and finally we obtain the velocity field at new time level n plus 1 as Vi n plus 1 is equal to Vi star star plus Pi delta t. Now, this is only one way of breaking the things up. The advantages of this breaking up are not that obvious in the context of explicit Euler method, but it would become a lot more apparent when we use an implicit scheme. One thing would still be common here with what we had seen earlier with explicit integration, that this Pi would be used only after we have solved a Poisson equation for pressure to ensure the satisfaction of the continuity equation. So, before we proceed for the last step of computations, we would have solved a pressure Poisson equation using these velocity components Vi star star. Now, what would be actual algorithmic form of a fractional step method? That would depend on our choice of discretization procedure, that is to say whether we have used finite differences, finite volume or finite element method, and in finite difference or finite volume method, what is your computational molecule or computational stencil, how do you want to handle this convective and diffusive terms, and so on. So, there are wide variety of choices. Similarly, it will also depend on our choice of the time integration schemes. Furthermore, we can split the convective and diffusive terms into their components in respective coordinate directions, and this can facilitate our computations, specifically when we use an implicit time integration scheme, wherein we have to solve a system of equations, a system of linear equations or linearized equations at each step. So, if you can break our diffusive and convective terms in respective coordinate directions, and if we use a certain type of stencils, it is possible for us to break each of these steps in fractional steps into system of tridiagonal equations, which can be solved very efficiently. And there is many different types of splitting are possible, which lead to a wide variety of fractional step methods. If you try looking into literature, you can find at least 100 variants, and let us discuss only one of these. We have already seen one based on explicit time integration. Let us see one based on an implicit time integration scheme, and this would be based on a second order accurate Crank-Nicolson method. The conceptual steps are that what we will first do is we will advance velocity using pressure from previous step, and we would obtain the resulting velocity V star. Now, next step what we will do is we would remove half of the old pressure gradient to obtain a new estimate V star star. Next, use this V star star to solve a pressure Poisson equation to get pressure at new time level, and then obtain the final velocity at new time level by adding the gradient of new pressure, which will ensure the satisfaction of the continuity equation. So, now let us have a look at the equations which are involved in this fractional step method based on Crank-Nicolson scale. So, let us get to a board to derive the appropriate equations. So, fractional step method based on Crank-Nicolson method. Now, this is just for the sake of illustration purposes, this is only one way. The similar approach can be utilized to obtain a wide variety of fractional step method, as I have just mentioned earlier. So, now our step 1, what do we do in step 1? We would use pressure at previous time level for advancement of velocity field. And remember, let us use our notation earlier. The earlier notation which we have used was shorthand notation which we have adopted for semi-discrete Navier-Stokes equation. We said we can write this as del of rho V I over del T is equal to H I minus delta P over delta X I, where this H I represents contribution from convective and diffusive terms. Okay. So, this was our initial equation. Now, we are using Crank-Nicolson scheme. So, Crank-Nicolson scheme involves the values at the new time level as well as the value at the old time level, and a simple average of the two. That is what is the basis of Crank-Nicolson method. Pressure, we do not know the new values, so we will use only the old values here. So, our step 1 becomes rho V I star minus rho V I n is equal to delta T times 1 by 2 H I V I at n plus H I at V I star minus delta T times delta P n over delta X I. Let us call this as equation 2. Now, remember here we have got the terms in V I star on both the sides. Okay. So, this would represent a system of equations which have to be solved to obtain the solution V I star. In step 2, what we would do is we would remove half the contribution which we have incorporated in equation 2 from the previous time level. So, remove half of the old pressure gradient from V I star to obtain V I star star, that is rho V I star star is equal to rho V I star plus delta T by 2 delta P n over delta X I. So, this is our second step. Now, final velocity field is obtained by introducing the gradient of pressure field at Tn plus 1, but that is still unknown. So, let us write down that in just theoretical format. That is what we would do, like to do is just write that Vi, rho Vi at n plus 1 is equal to rho Vi star star minus delta T by 2 delta P at n plus 1 divided by delta Xi. Let us call this as equation 4. Before we can use this formula to compute Vi n plus 1, we ought to know what is P n plus 1. So, how do we do that? For that, let us derive a pressure Poisson equation. So, Vi n plus 1 must satisfy the continuity equation. Hence, let us take divergence of 4. So, what do we get? Del over del Xi of rho Vi n plus 1 is equal to del over del Xi of rho Vi star star minus delta T by 2 del over del Xi of del P n plus 1 over del Xi or delta Xi. LHS must be 0 because Vi n plus 1 must satisfy our continuity equation. So, let us rearrange, and this will give us the discrete Poisson equation for pressure, that is del over del Xi of delta P n plus 1 over delta Xi is equal to 2 by delta T delta over delta Xi of rho Vi star star. So, this is Poisson equation for pressure at the time level n plus 1, or rather P n plus 1. So, now we have got all the equations with us. So, in fact, our steps would be step 1 we have already seen, that advance the velocity field using the known pressure value, that was a step 1. In step 2 we removed half the old pressure value, so thereby we obtained this Vi star star. Next we use this Vi star star in pressure Poisson equation to solve for P n plus 1, and then add its effect to Vi star star to get the velocity field at time level n plus 1. So, that is whatever actual algorithm, fractional step algorithm is. Okay. So, these were formal steps, that is advance velocity using pressure from the previous time step, we obtained the resulting velocity which we called V star, and then from this velocity field V star we removed half the old pressure gradients to obtain a new estimate V star star. Now, this was used in the derivation of the pressure Poisson equation. Okay. So, take divergence of this, use it as a source term in the pressure Poisson equation, and solve the pressure Poisson equation to get the pressure at new time level. Then to obtain the final velocity at new time level, we have to add the gradient of new pressure into V star star, and that completes our solution process at the given time step. So, this way we would put a full stop to our discussions on the fraction step methods. There are quite a few other interesting algorithms for the integration of incompressible Navier-Stokes equations. When we had our discussions, we saw that the conceptual solution of compressible form is very simple, because we had the appropriate number of equations. Pressure was obtained from the equation of state. We had one equation continuity for density, 3 momentum equations for the velocity component or the related fluxes rho u, rho v and rho w. Then we had energy equation and we solved it and we got our solution field. Can we use a similar thing? So, they say that technique which is called artificial compressibility method, wherein the continuity equation is modified to incorporate that artificial compressibility for incompressible flows, and we can use a similar solution process as we had used in the case of compressible flows. So, that is yet another way of solving incompressible Navier-Stokes equations. So, I would encourage you to look into these nice books. The first one is Anderson J.D. Computational Fluid Dynamics Basics and Applications. This book deals particularly with aerodynamic applications. So, you will find very beautiful discourse on very simple time integration schemes for compressible flows in the context of finite difference spatial discretization schemes. Chung's book on computational fluid dynamics, that is a compendium of almost all known schemes till 2010. It has got discussions on solution of Navier-Stokes equation using finite differences, finite volume, finite element techniques, and plethora of the time integration schemes for both compressible as well as incompressible flows and their applications. So, you can refer to this book. And Fersigers and Perrick book is at another one, which provides a very nice introduction to computational method for fluid dynamics. And if you are interested only in finite volume method, Versteeg and Malala-Sekhar's book gives you a very good introduction to the application of finite volume method in solution of CFD, specifically in solution of Navier-Stokes equations and the solution of advection diffusion problems. So, with timing, this way we would stop as far as this course is concerned in connection with Navier-Stokes equations. In the next module, we will take up application of what we have learned so far for solution of turbulent flows.